Derivation of the least squares formulas. These formulas are used in data analysis, and in this video we will see exactly where these formulas come from. We will start with Excel, and the example or motivation that we will have is a simple linear relationship called Ohm's law, which we remember is voltage equals to current times resistance. Say, for example, we go ahead and run a quick experiment in which we have, say, a 50 ohm resistor, and we measure the voltage as we ramp it up from 10 volts all the way up to 14 volts in half-volt intervals, and we measure the current in amps. So in this case, that would be 205 milliamps and so on up to 281 milliamps. And then we plot voltage versus current on the x-axis. Now, if we want to go ahead and do the trend line or the least squares best fit line over this set of linear data, in Excel, we know that we can go ahead and click on the data and select over here chart design, add chart element, and we look for trend line. We know that this is going to be a linear relationship, so we don't select any of the other options but the linear option here. And we see that we have a trend line here. Now if we click on this trend line, we get this menu, and one of the options that we're going to be keen on is display equation on the chart. So once we have that, we can close that, and we can go ahead and make this a little bit easier to read by increasing the font, and we see the following. We see that we have an equation of the form y equals to mx plus b, m being the slope, which in this case would be the resistance R. So remember we had a 50 ohm resistor across, but because we essentially read current that was a little bit off, a few percent higher or lower, the best fit line tells us that the resistance is actually 46.398 ohms, and the Y-intercept would be 0.849. So that would be the voltage intercept right here. It's not actually zero because, again, of the measurement error. So that is how we use the least squares analysis in a plotting package and data analysis package, actually, such as Excel. The question is, where does this come from? How do we get from x's and y's, here, all these values of x and y, to a value of m for slope and b for y-intercept? Where do these values come from? So that's what we're going to find in the next portion of this video. We start with the equation for a line, y equals to mx plus b, and we introduce the subscript I to indicate our individual data samples. Now what we want to do is we want to go ahead and put everything on this side of the equation. So we say y sub I minus m x sub I minus b equals to this e sub I, or error term. Notice that this is going to be positive and negative. So what we want is for this term to always be positive. So we're going to square it, hence the name least squares. And we define this function of m and b as the following. This is equal to the sum I equals 1 to I equals n of this quantity squared. So that would be y sub I minus m x sub I minus b quantity squared. When we go ahead and write out this term, we have I equals 1 to n. Again, n is our total number of samples, and we end up with these quantities squared plus some additional cross terms. So let's write it out. Y sub I squared, the minus, since we're squaring, becomes a plus, m squared x sub I squared plus b squared, and here come the cross terms, minus 2m x sub I y sub I minus 2 b y sub I, and last plus 2 b m x sub I. These sums can then go ahead and be written down as sums of the independent terms. And instead of writing I equals to 1 to I equals to n, we just say sum over I, y sub I squared, plus sum over I, m squared, x sub I squared, plus sum over I, b squared, minus sum over I, 2m x sub I, y sub I, minus sum over I, 2 times b times y sub I, plus this last term, sum over I, 2 times b times m times x sub I. So far so good, just a messy expression, but now we let big X be defined as sum over I little x sub I, and big Y be defined as sum over I little y sub I. And we introduce three terms that are going to be defined as follows. The reason we're doing this step right here is to go ahead and help with the housekeeping, so we don't have to write this enormous expression. This is going to be sum over I little x sub I squared. This is going to be sum over I little x sub I times little y sub I. And C is going to be sum over I y sub I squared. So now we can write this expression in terms of x, y, a, b, and c, and one last term, which is going to be the total number of terms. So for that, we write down e of mb again, but hopefully in a more manageable form. We write this as c plus m squared a plus b squared n, and this is the total number of samples, and minus 2m uppercase b, and be careful not to confuse that with lowercase b, minus 2 little b big Y plus 2bm big X. So far so good. We've just rewritten the previous expression. At this point, what we're going to do is take a partial derivative with respect to this variable m of our function e of mb. Notice that we're essentially varying the slope, changing the slope to see which slope is actually going to fit our data the best. That's where this term comes in. So taking this partial derivative with respect to m becomes a little bit more manageable. This becomes 2ma minus 2b plus 2bx. And since we're looking for the least error, or an extremum, we're going to go ahead and set that equal to 0. Similarly, we take the partial with respect to little b of our function. So we're optimizing our line essentially to make it fit in an optimum way with least errors the data points, the line made by the data points. So that's 2bn minus 2 big Y plus 2m big X. And again, we set that equal to 0. Expression number 2, we go ahead and write it down here and do some manipulations. So that becomes, well, let's write it down. 2bn equals to 2y minus 2m big X. We divide by 2n. And do some cancellations. And this implies a value for little b, which is our y-intercept. This is equal to y, big Y, minus m, big X, divided by n. We go now to expression number 1, and we write it down again with some manipulations. 2ma equals to 2b minus 2. And here we have this quantity here. So what we're going to write is y minus mx divided by n times big X. Now we can divide by 2a. And we do some cancellations. 2's cancel there, 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 and here we can cancel the the a. So this implies that we have an expression for m. M equals to big B over big A minus yx over na plus mx squared over na. Now we go ahead and isolate a little bit of another another step here. 1 minus x squared over na is equal to bn minus yx over na, which implies that m, well, actually we can say one more step over here. Yeah, one more step over here. We can say that m times na minus x squared over na. So we just rewrote that step right here. So then we can say that m equals to bn minus yx over na minus x squared. We've essentially divided one by the other. The na's canceled. So these two expressions then are exactly what we were looking for. An expression for the b-intercept and an expression for the slope. So all is good. So as a final step, what we're going to do is we're going to just substitute our sums of x's and y's into those two expressions. We end up with m equals to big N, or the total number of samples, sum over I, x sub I, y sub I, minus sum over I, little x sub I, times sum over I, little y sub I, divided by n, sum over I, little x sub I squared, minus quantity sum over I, x sub I squared. And similarly, we say that b equals to 1 over n sum over I, little y sub I, minus sum over I, little x sub I, times this term up here. And there we have n sum over I, x sub I, y sub I, minus sum over I, x sub I, sum over I, y sub I, divided by n times sum over I, little x sub I squared, minus quantity sum over I, x sub I, quantity squared. So this is what we're after. These are our two formulas for the m and the x the m and the b quantity. So that defines our slope and y-intercept depending on, or as a function of, the total number of samples and some sums of our data points. So we should now be able to see where these come from. Going back to the Excel spreadsheet, and this time coming up with sums of our x's and y values for our data in a manual manner, so that we can say, for example, the parameters x, y, a, b, c, and n are actually derived by summing in Excel the x sub i's, the y sub i's, the x sub i's, and then squaring them, and then the x sub i's times the y sub i's, and lastly the y sub i squared, and n being the count of data points that we have, and substituting them into our equations for little m being this, which is what we derive. We come up with a value of, again, you see the entire sum up here in the formula line, 46.398, which is exactly the m value that Excel's trend line least squares analysis gives. Similarly, the little b is 0.849, just like Excel said. So this is a way to actually understand mathematically, using calculus optimization, how these values actually come about. And this is the derivation of these formulas that we consider least squares formulas for data analysis that we see printed in many places, but wonder maybe where exactly they came from. Well, hopefully this was helpful.